Good evening, friends. Study with the Pala Engineering and Journal Geology Parvin Singh book. So in chapter 9, dispersion, study of mineral, 9th chapter हमारा चल रहा है. This is a phenomenon, so depending on the refractive index of a substance. Ordinary light, as we know, is made up of a spectrum of 7 type of radiations, so violet being at one end and the red at the other end of a spectrum. So when a medium is capable of breaking the light into its component colors during transmissions as a prism of glass, each component is refracted at a characteristic rate which is different from that of the adjoining radiation. The net result is a difference in the velocities of the component colors radiations with the body of the medium. This difference in the index of refractions for the various radiation result in a brilliant. This is a characteristic property of a gem. Higher the refractive index, greater is the dispersion of light. And for example, in diamond, the red end of spectrums has a refractive index of 2.407 and the violet and 2.465, difference 0.058 being of a very high order. Total reflection in the property of light, that when is passed from the denser mediums to a rare mediums, example from the water to air, it get refracted away from the normals. In all such cases, a stage is reached when at a particular angles of incidence, so the angle of refractions is 90 degree. This angle of incidence is called critical angles. All the incident rays impinging upon the mediums beyond these angles will be reflected backwards into the mediums rather than getting refracted. The phenomenon of reflections of an incident ray back into the same medium is called total internal reflection. It has been established that substances of a higher refractive index have lower critical angle and vice versa. So the critical angle of diamond, for instance, is 24 degrees to 24 degree 26 minute with respect to air. So in figure, total internal reflections, incident ray W is reflected back as a ray X. Double refraction is a calcite cleavage plate ordinary ray O is doubly refracted into A and E. Double refraction. It is one of very significant properties of some solids, especially minerals, and has proved highly useful in their identifications. When a ray of light passes through such mineral, it is not only refracted but also resolved into two rays, each having its own velocity and hence separate index of refractions. All minerals and artificial crystallized substances expect those crystallizings in cubic systems show this property of double refraction. The two rays resulting from the single incident ray are designated as ordinary ray symbols A and extraordinary ray symbol E in a small indication. It is characteristic of A that it has a small velocity in all directions. In a given substance, while the extraordinary ray E has a different velocity in different direction. In the same substance, again, since say some minerals, the velocity of though constant may be higher than that of E, whereas in others minerals it may be E which has a higher velocity. This factors gives another basis for optical classification of minerals by fringes. This is a phenomenon related to the property of a double refractions. Each of the two rays, ordinary A and extraordinary E, will have its own refractive index with respect to the same medium. The difference in the refractive indices axis of these rays is expressed by the terms birefringence and indicates the degree of double refractions in a substance. Isotropic substance. Those substances which do not show the phenomenon of double refractions are called isotropic. In these, the refractive index of light is uniform in all directions. Mineral belonging to isometric systems are all isotropic in character. Some examples are diamond, garnet, halite, and galena. An isotropic substance. When a substance such as a mineral shows double refractions, that is, in which an incident ray of light is broken into two rays which travels with a different velocity, thereby causing a variations in the property of refractive index in different direction. It is called an isotropic. Minerals belonging to all crystallographic systems except cubic system are an isotropic in character. Quartz, calcite, fluorite, gypsum, tourmaline, and topaz are just a few examples out of hundreds of such minerals. Optic axis. It is the directions in an isotropic substance in which there is no double refractions. This term is relevant only in an isotropic substance because in isotropic substance double refraction does not occur at all. In isotropic substance there may be one or two such directions in which the phenomenon of double refraction is not observed. These directions are expressed by the terms optic axis. Minerals are further distinguished as optically uniaxials if there is only one optic axis and optically biaxial if there are two optic axes and directions or of no double refractions. The minerals crystallizing in tetragonals and hexagonal system are optically uniaxials, whereas mineral crystallizing in orthorhombic, monoclinic, and triclinic systems are optically biaxial. Optical science, whilst studying optical properties of a mineral in thin sections under a microscope, it is also usual to determine its optical science, that is whether it is optically positive plus and or optically negative minus. This is done on the basis of the relative velocity of the two rays into which the incident ray is resolved on double refraction. In uniaxial minerals, a mineral is said to be optical positive if the velocity of ordinary rays A is greater than that of extraordinary ray E. It is the same thing as saying the refractive index of extraordinary rays is higher than that of ordinary ray because a refractive index is reciprocal of velocity of the ray. Optically negative if the velocity of the extraordinary ray is greater than that of the ordinary ray. In the biaxial minerals, there are three vibrations directions distinguished of as a X factor and Y intermediate and Z slowest, with the corresponding refractive indices as alpha, beta, and gamma respectively. In order to determine the optical signs of such a mineral, following considerations are kept in mind as there are two optic axes, as these may be inclined to each other at an angles called the optic axial angles, which may be acute or obtuse, as X or Z vibration direction may be the bisectric of the optic axial angle. A biaxial minerals is described as optically positive if Z is the acute bisectrix and optically is negative if X is the acute bisectrix. Thank you.